Comet 3I/Atlas, officially designated C/2025 N1 Atlas, has rapidly become one of the most scientifically fascinating objects observed in 2025, not because it poses any threat, but because of what it represents: a rare visitor from beyond our solar system. Only two interstellar objects, Oumuamua in 2017 and 2I/Borisov in 2019, were confirmed before it, making 3I/Atlas just the third known example of material from another star system passing through our cosmic neighborhood. Each such object offers a once-in-a-generation opportunity to study matter formed around a different star, preserved for billions of years, and now briefly illuminated by our sun. Over the past several weeks, a surge of new observations across optical, infrared, and X-ray wavelengths has transformed 3I/Atlas from a distant curiosity into one of the most intensively monitored comets of the year, sharpening scientists' understanding of both its physical behavior and its broader significance. As public attention has grown, so too have misconceptions, particularly on social media, where dramatic headlines can easily blur the line between rarity and danger. NASA and other space agencies have been unequivocal in their assessment. Comet 3I/Atlas poses absolutely no risk to Earth. Even at its closest approach on December 19, 2025, the comet will remain about 1.8 astronomical units away, roughly 270 million kilometers or 170 million miles. To put that distance into perspective, Earth orbits the Sun at 1 astronomical unit, meaning the comet will stay nearly twice as far from us as the Sun itself. This vast separation ensures that the comet's passage is purely an astronomical event, not a planetary hazard, and any concerns about collisions or catastrophic effects are entirely unfounded. What has truly captured scientific and public interest instead is the comet's evolving appearance, particularly a noticeable shift in color. Earlier in 2025, 3I/Atlas appeared relatively red or neutral in tone, consistent with a dust-dominated coma reflecting sunlight. More recent images, however, reveal a faint but distinct greenish glow surrounding the nucleus. This change is not cosmetic in the casual sense. It is a physical signal that the comet's chemistry and activity are evolving as it responds to solar heating. Comets are often described as dirty snowballs, but that phrase barely hints at their complexity. Beneath a surface crust of dust and organic material lie layers of frozen gases, water, carbon monoxide, carbon dioxide, and more exotic compounds that can remain locked away for eons. As a comet approaches the Sun, heat penetrates inward, causing these ices to sublimate directly into gas, dragging dust along with them and forming the coma and tail. In the case of 3I/Atlas, the green glow is widely attributed to diatomic carbon, known as C2, a highly reactive molecule that emits green light when energized by sunlight. This phenomenon is not unique to interstellar comets. Many long-period comets from our own solar system display a similar green coloration at certain stages of their journey. What makes it particularly intriguing here is the context. Because 3I/Atlas originated around another star, its composition reflects a different protoplanetary environment, shaped by alien radiation fields, temperatures, and chemical histories. The emergence of C2 after the comet's closest approach to the Sun suggests that solar heating has reached deeper layers of the nucleus, unlocking volatile compounds that were previously hidden beneath the surface. Timing is crucial to understanding why this matters. The images drawing attention now were taken after the comet's late October perihelion, its closest point to the Sun. This period is often described by comet scientists as a kind of thermal stress test. As a comet swings past the Sun, it experiences intense heating that can crack surface layers, open new vents, and expose pristine material from the interior. Some chemical signatures do not appear immediately at perihelion, but emerge weeks later, as heat continues to propagate inward. In this sense, the green glow of 3I/Atlas is a delayed response, a visible sign that the comet is still adjusting to the solar encounter and revealing new aspects of its makeup. Beyond visible light, 3I/Atlas has also become the target of an unusual multi-wavelength observing campaign, including detections in X-rays. While X-ray emission might seem surprising for a cold, icy object, it is a well-understood process in cometary science. When neutral gas escaping from a comet's coma interacts with the solar wind, a stream of highly charged particles flowing outward from the sun, charge exchange reactions can occur. In these interactions, electrons jump from the comet's atoms or molecules to solar wind ions, producing X-ray photons in the process. Observing these emissions allows scientists to study both the composition of the comet's gases and the properties of the solar wind itself, effectively turning the comet into a natural probe of the space environment. For an interstellar object like 3I/Atlas, such observations are especially valuable. Unlike comets that formed within our solar system, whose compositions can be compared against a large existing dataset, interstellar comets offer a rare external reference point. By measuring how its gases interact with the solar wind and how its activity evolves with solar heating, researchers can test whether fundamental cometary processes are universal or whether they vary significantly from one star system to another. Early indications suggest that, at least in broad terms, 3I/Atlas behaves remarkably like comets we already know, forming a coma, releasing familiar molecules, and responding predictably to solar energy. At the same time, subtle differences in the timing and relative abundance of emissions may hint at a distinct formation history. The green glow itself carries symbolic weight beyond its physical explanation. It serves as a visual reminder that this object is not static, but alive with processes unfolding in real time. Each change in brightness or color represents a shift in temperature, chemistry, or structure within the nucleus. For astronomers, these changes are data points. For the public, they are a rare chance to witness the dynamic nature of an object that spent untold ages drifting through interstellar space before briefly encountering our sun. The fact that such an object can be detected, tracked, and analyzed across multiple wavelengths speaks to the remarkable capabilities of modern astronomy and the global coordination among observatories. It is also worth emphasizing how quickly understanding has evolved. Just days or weeks of additional data have refined orbital calculations, improved distance estimates, clarified chemical signatures, and dispelled unfounded fears. This rapid progress reflects both the urgency and the excitement surrounding interstellar objects. Because their trajectories carry them swiftly through the inner solar system, there is a limited window in which to observe them in detail. Every new dataset adds to a collective effort to extract as much information as possible before the comet fades and continues its journey back into interstellar space. Ultimately, Comet 3I/Atlas is important not because it is green, bright, or dramatic, but because it is a messenger. It carries with it a physical record of another planetary system, encoded in ice and dust, and now briefly readable through telescopes and detectors. Its safe passage at a great distance from Earth allows scientists to study it without concern, focusing instead on what it can teach us about the diversity of planetary formation across the galaxy. As observations continue through the end of 2025, 3I/Atlas is likely to remain a benchmark case, a reminder that our solar system is not isolated, but part of a larger, interconnected cosmic environment through which such travelers occasionally pass.